Okay, I want to first look at the idea of something called a probability density function, which is we'll introduce the notion of a random variable, which we've already actually seen. But let's consider an example of a dichotomic variable. This is sometimes known as a binomial random variable, binomial PDF or probability density function. So roughly true, about 10-11% of the population are left-handed. About 90% are right-handed. So imagine I've got a dichotomic variable. There's people that are ambidextrous that can do both, and of course, I'll just look at this as a case where it's only two values possible. So take a sample of 1,000 people. I measured an absolute frequency. Just say, for example, I wind up with 890 who are right-handed. Let's call that variable x is equal to 1. And there'll be 110 that are left-handed. Variable x is equal to 0. And this is relative. I could look at it in terms of relative frequency or absolute frequency. There's nothing particular new here. We've seen this before. Now, what would happen if I increased it to not 1,000 people? My sample size, n is equal to 1,000,000 people. Well, it's going to change a little bit, but it's going to be roughly like this, more or less. Of course, the absolute frequency numbers would be different. Let's consider another case, this case a discrete variable. Now, we saw this before as a uniform distribution where I roll a fair die. You can get, roll it 1,000 times. You roughly get about 160, 170, 180, something like that. It depends. It's going to go up and go down a little bit. As you see, I think I actually did a Monte Carlo experiment. You'll notice the blue lines are a little bit different. I did this with Excel, and if you, of course, you change it, you'd always get different results. What happens if I rolled it a gazillion times? Now, this is like 1,000,000 times 1,000,000. It's a big number. This is sometimes referred to as the law of large numbers. It actually comes in two versions. But the basic idea here is that if you do this many, many, many times, it should settle down. If it's the uniform distribution, it should settle down to, in effect, 1/6. And you'll notice on the left-hand side now, I've said that relative frequency turns into probability. And that's one definition of the law of large numbers, assuming that n is really, really big. And there's an issue there about how big does it have to be before it settles down to set numbers. Okay, so what if I do the same thing with a continuous variable? Here I've got x. We made the case of 200 women, for example, between, I think these are exactly the same, it's 55 to 58 inches, 58 to 61, and so on. So these are the numbers we had before. I forget what they were exactly. I think there was like 2 people between 55 and 58, 4 between 70 and 73. Anyway, we've seen this number. So you'll notice here I've gone to relative frequency. I could put it with absolute frequency on the other side. We have a problem with a continuous variable that doesn't arise with a discrete variable. And you'll see it in a second. See what happens if instead of having cells, here we had the example of 55 to 58 inches, so 3 inches for each group, if you will, cell. But if I now divide them into cells that are only 1 inch and not 3 inches, you can see what happens to the relative frequency. It falls. It gets smaller. It makes sense because there's a number of women that are going to fall between 55 and 56 is going to be fewer than between 55 and 58. So the problem with a continuous variable is that this idea of relative frequency is dependent on the size of the cell, how large the grouping is. Of course, now you could increase the number of women, but that wouldn't really solve the problem because the relative frequency refers to the number of women, or the percentage of women that fall within a particular group. So that wouldn't solve the problem. I'm going to illustrate this problem in a slightly different way, make it a little bit easier maybe to understand using the notion of a uniform PDF. But keep in mind this is a continuous random variable. So imagine you're thought of this example in Italy, but in Italy there's lots of mountains, lots of valleys, and as a result there's lots of bridges and lots of tunnels. So imagine you're driving on one of the autostrada. They've got markers all the way along. So it's got kilometer marking distances, and you're about to drive. This is neat in Italy too because they have a little sign at the entry to the tunnel telling you how long it is. So imagine you're about to enter a tunnel. It starts at, you're driving from Milan to Rome. It's at the 102.5 mil born, the kilometer marking. It's 500 meters long, so it's going to be 103 meters when you leave. And the issue now is, well, what is the chance of your car breaking down inside the tunnel? Now, keep in mind, this is a continuous variable because you could break down anywhere. So it's not like discrete. So let's take a look at this idea. I've done the same thing. I've got the kilometer marking X. We've got relative frequency along the top, and I've got a tunnel that starts at, 500 meters, 102.5 to 103. Now, what is the chance of breaking down in the tunnel? Well, let's be a little bit more precise about that. What is the chance of breaking down in the first part of the tunnel or the second part of the tunnel? So it's sort of like saying specifically in the first 250 meters or the second 250 meters. I say, well, if it's uniform, 50-50 chance. So the relative frequency of cars breaking down in the first 250 meters, second 250 meters is going to be 50%, 50%. Fine. But what happens if I break it down? Here I've got cells that affect a distance of 250 meters. What happens if I break that down into cells of 100 meters? Well, now I've got a cell 100 meters, 100 meters, 100 meters. There's going to be 5 of them, and equal chance to break down in any one of those sections. So we could sort of say the chance relative frequency is 0.2, or 1 out of 5. I could further subdivide it as much as I wanted to. Well, let's drop it to 50 meters, 50 meters, 50 meters. So now I've got 10 little sections, if you will, along the roadway, little markers. What's the chance of breaking down in any one of these? Well, it's going to be, there's 50 meters. The whole thing is 500 meters. That's one chance in 10. So the relative would be 10% or 0.1. Now you can see what's happening here. It's the same problem we had a moment ago with the heights of women, is as we make these distances on the road smaller and smaller, the chance of breaking down in that particular segment is going to get smaller and smaller. This is the kind of thing that drove the ancient Greeks crazy, because at the limit, if you think about it, point at a particular point, the chance of breaking down at that particular point is 0. Well, that doesn't make any sense. So, without getting into the mathematics, how this is solved, Isaac Newton and Gottfried Leibniz kind of solved this problem in the 17th century. It involves calculus. I'm not going to go there, but you sort of see the problem. Okay, so the way we overcome this issue in probability theory, or in statistics at least, is to introduce a new concept of something called relative frequency density. See, I mentioned the word density here. So the idea of relative frequency density is that I take the relative frequency and I divide by the cell width. If you imagine the cell width is 50 meters, that's 0.05 of a kilometer. The relative frequency is 0.1, so I can now say 50 meters is 0.05 kilometers, and I can take 0.1, which is the relative frequency, divide by the cell width, 0.05, tells me the relative frequency density is equal to 2. Now what? I'm going to go back and take a look at the previous examples where I had different segments of different lengths and see what happens here. In this case, I had 100 meters, so if I looked at the relative frequency density, which I said was equal to the relative frequency, which is going to be 0.20 divided by, this case, 100 meters is 1/10 of a kilometer. It's still equal to 2.0. How about the other example I had? 50-50. So now the relative frequency density, I'll just write it as RFD like this, is going to be 0.50. That's the relative frequency in this case, and I'm going to be dividing this by 0.250, which is equal to still. So what this means is the notion of relative frequency density is invariable to however I define the length of the segment. I can make 250 meters, 50 meters, 100 meters, whatever I want. Relative frequency density will always be equal to 2. So I'm going to graph this now on the next chart, where you'll notice here I've got relative frequency density on the vertical axis. You'll notice equal to 2.02. And I've got the tunnel, 102.5 to 103. And you'll notice something else that's very relevant here. If I take the distance in kilometers, 0.5, and multiply by 2, it means the area here is equal to 1. Very important result, because it means like saying, well, there's a 100% chance if you're going to break down, it's going to be in the tunnel somewhere. That's 100%. But what's really relevant, if I want to find out the chance of breaking down, say, in this area here, all I have to do is find out what portion of this area here represents the part of the whole. If it's 40%, then you can say there's a 40% chance of breaking down in this portion here, in this segment. We can understand that very quickly because this is uniform. So all I have to do is know what the area is, 30%, 40%, 50% of the percentage of the whole, and we can say now we understand what the chance, and it's invariant to whether the Little point about this too, you sort of imagine, is what is the chance of breaking down at a specific point, like right here? Well, since the area underneath this line is 0, the chance of breaking down at that particular point is also 0. Now, I want to next apply this to, we've seen this before, the idea of a normal or bell curve, or something called the Gaussian. Same principle, where imagine now I had a curve. It's not exactly perfect, but it's pretty close. Imagine heights. We can say the same thing. The area underneath it is 1. And now, it doesn't matter whether I make the cells really, really small or really wide, it will still apply. And we'll notice I've got relative frequency density on the vertical axes here. So it may sound strange, but there is an actual equation for this curve. It's not by chance that people's heights tend to follow it. And we're going to look at this later in the course about why that is. But for the moment, just assume there is a curve. I think I'm going to give it to you in the next screen. Yeah, here I've kind of drawn it out so it's smooth. Here's the actual equation. And you'll notice a couple of things distinct about this equation. There's this E, which is that number that's natural E, 2.71 something, something, something. And you'll notice something, this pi here, that's the pi that everybody knows is 3.141592, blah, blah, like that. Clearly, this equation is a very important equation in the universe. And this curve is, this equation is not, it isn't just invented like this. There's a reason why it is like this. This is the general form, and I think I put in the specific form. Yeah, I just left it. Once again, if we look at 50-50, so everybody knows the R-score. It follows the normal distribution, centered on 25 with a spread of 5. Notice I'm using mu as the population mean. Sigma, that's the second moment, tells us how spread out the numbers are. Incidentally, the Ministry of Education in Quebec sets it like that, so that it follows the normal distribution, this bell curve, this Gaussian, where the center is 25. That means the average R-score of everybody in Quebec is 25, but it's got a spread of 5. They manipulate the numbers to make sure that's the case. So, for example, if I want to find out what is the chance of somebody, a student, I don't know what their R-score is before I ask them, is it greater than 25? Well, it's a 50% chance. Is it less than 25? 50%. But I might be more interested to find out what is the chance of this. We would write it like this. R is, I could put over here, R is the random variable that follows that normal distribution centered on mu, the population mean, and with a spread of sigma. What we're going to be very interested in is to find out, let's say I pick a number like 30. So I'm curious to know what is the chance of a student having an R-score greater than 30? Well, what I'd have to be able to do is find out the area here. I know the whole thing is 100%, so I'd have to find out the area here. Now, when we did it before with the uniform, it was kind of look at it, you could sort of guess it. Here, I don't know, just looking at it, what would you say? About 20%? Somewhere around that, 20, 25. I don't think it's twice. This area here of the whole, maybe 15. 10% maybe? I don't know. In a second, you'd need this equation, and you'd have to know what's called antiderivatives or integral to be able to find out the area underneath a rounded curve. There's formulas that do that kind of calculation, and that's what we'll be using later in the course. There's a little app with Moodle that does this kind of thing. It's very easy to use. But obviously you could do it by eye, just by looking at it. I think it's about 15, 20%, something like that. But the basic principles, the area under the whole thing is 100%. And if I want to find the area, of course, the area on this side is going to be whatever this one minus that. There's a very commonly reported normal distribution, bell curve, normal curve, which is referred to as the Z distribution. And so this one here, Z, is indicated like this. I've given the formula for it. I don't know if in this case here, you can imagine that I've got the averages, mu here, which is going to equal to, and this is equal to sigma. This is equal to 0, and this is equal to 1. And so this is sometimes referred to as the standard normal. It's the one often, it's not as referred to as the Z-score. It simplifies down because, in effect, what we're saying is the mean is 0 and the spread is equal to 1. There's no reason why this is more important than the R-score happens to be 25 and 5. There's many different versions of it. Got these little factoids at the end here. This equation clearly is very important because, as I said, it's got the two key real numbers, natural E and pi, which obviously have some kind of significance in the universe. And then, in addition, this is, I believe, the only PDF. for a continuous variable where the third, fourth, and higher moments are all equal to 0. So that means only the first two have to be, and sigma always has to be non-zero.